Hi, students. It is Mrs. Armstrong. I am going to go through a little bit of lesson 3 and lesson 4 in this video. I will eventually want you to watch the video for lesson 5, but after you complete these problems in your notes packet, depending on which class you were in, we either did problem 3 or you didn't. If you were in the class that did problem 3, you can move forward unless you need a recap or you were absent. It's always good to just kind of go back and take the notes. For problem 3, um, looking at this, are these two triangles similar? Go ahead and take a moment, pause this video, read through the problem. Okay, so Erica thinks the two triangles might be similar. However, she knows not to trust the way the figure looks in the diagram, so she asks for your help. A, are the two shapes similar? What must be true about their angles and sides? So, looking at the surface, yeah, maybe these are similar, and if they are, then the angles have to be the same, and the sides must be proportional. So we talked a little bit about proportionality last week. That just means, if this is 4, then, and this is 2, right? Then you are multiplying by half, by a scale factor of half. So if this is, 2, and then this has to be 1 by definition because you have to multiply again by a half. So you have to have the same scale factor or be dilating by the same in order for it to be proportional. Um, so then for part B, the resource page, it would have just been an enlargement of those two figures. And then you would have used your protractor to measure the angles. And in this case, you'll notice that the angles are actually the same. So if we are looking at this triangle, forgot what the angles were. I want to say when we measured, again, I'm just going off the top of my head, but it was 110 degrees. And then I think like this angle was 30 degrees and this angle was 40 degrees. And again, if you measured, you would have had the same angle. So looking at this, you probably noticed right away, like, hey, all the angles are the same. Um, and if that's the case, then yes, these two triangles are similar. Um, so then for part C, assuming that the corresponding sides of these similar triangles are parallel, demonstrate there is a dilation that carries one onto the other by finding the point of dilation or the stretch point for the two triangles on the resource page. So, you could mark this point here, and then, kind of draw that line from here to here. Um, and that stretch factor again would be dependent upon what the measurement of those sides are. Okay, so you have your stretch factor right there, although that's not like the best way for me to show you the point of dilation, but yeah. Okay. We didn't really get too much, honestly, into the depths of part C, so as long as you established A and B, you were good. For problem 4, we have Joven is tired of measuring all of the angles and sides to determine if two sides are similar. There must be an easier way, he thinks. What if I know that all the angles are congruent? Does that mean the triangles are similar? Do you think that triangles have to be similar if all 3 corresponding angles are congruent? You can pause the video and take a moment to think about that. Okay. So you would obviously write your response. Yes, if the triangle has corresponding angles that are congruent. And congruent just means similar and equal to. Then the triangles are similar. Okay. Going on to part B, experimenting with Joven's idea. You would use that tool to make a triangle with angles 38, 62, and 80. How can you make another triangle with the same angles that is not similar to your original triangle? Can you create any two triangles with the same three angle measures that are not similar? So if you tried to draw any two triangles that are different but have the same angle measures, you wouldn't be able to. They would still be similar in shape but not in size. So the shapes would be similar but not the same size. Okay. We're gonna skip part C just in the interest of time. Um, looking at problem 5, this is probably the more important problem, and I would really encourage you to, pause your video here and, read through this, and see if you can answer it, yourself. But for problem 5, we have these two triangles. You'll notice that these two angles here, G and J, are the same. So, looking at this, right, if you were to measure your missing angle, you would get 25 here and 68 degrees here. But before that, if I found one of the angles 25, like, well, these two are the same. So then, therefore, by default, this has to be 68 degrees, right? So for part A, are the corresponding angles equal? We would say yes. If we found the missing angles using and this is a famous theorem, you all used it last unit, it would be the triangle sum theorem, and I'm just abbreviating here. All angles are equal. Okay. For part B, how many pairs of angles need to be congruent to be sure that the triangles are similar? And the answer is you only need two congruent angles in a triangle. And the reason we only need two congruent angles is because by definition of triangle sum theorem, the third angle would have to add up to 180. So, and then for how could you abbreviate the similarity condition? We call this AA. And then this is a symbol for similarity. So this would be angle similarity. So basically what all this is saying is that if you have two angles in a triangle that are the same, then you can say that the two triangles are similar by angle similarity. Okay. So that should get you all the way through page 16. I think we end up skipping problem 6. And if you look at problem 7, again, it's just kind of reestablishing. Oh, wait, nope, we did not skip 6. 6 is actually really important. I'm sorry. Let's go back to that one. I don't think we got to this one last time, so this is definitely one you'll want to review. So for problem 6, what if we know that one angle is congruent, but the two pairs of corresponding angles that make the angle are proportional? Does that mean that the triangles are similar? So again, we'll use this tool. that's linked here, but I'm not going to show it on the screen right now to test the two triangles. If we were to basically have these two triangles and create a second triangle, that like this, where we have 4 centimeters, 20 degrees, and 5 centimeters, or even something that's, you know, um, I'm sorry, that is proportional. So let me erase this. If we had, 8 centimeters and 10 centimeters, right? We could say that these two triangles are similar. Because 4 goes to 8, you're multiplying by 2, 5 goes to 10, you're multiplying by 2, and then they have this common 20-degree angle in between the two sides. So if the 20 degrees was off to here, then this wouldn't work. So again, you would kind of test those ideas in B and C. But we're actually going to jump to problem 7 here. For this one, looking at problem A, in order to confirm that those two triangles are similar, we would have to try angle-angle similarity. For problem B, we would have to test out side angle side similarity, which is what you were kind of doing in the last problem, was side angle side. So for these two triangles in part B, for example, this would not work because 120 does not equal 90. So for side angle side similarity, you would not be able to establish that these two triangles, this one and this one, are similar because you have the angle degree in between them that are not the same. For part C, I know this one is a little trickier. You have two triangles on top of one another. You have one right here, and then you have a large one right here. So you can either use side angle side, but you would need to know the side measures, and we don't. So we can actually use angle similarity because the two triangles share that angle that I just drew. So this would be angle similarity. And then for part D, there is not enough information at this time. We'll talk more about side similarity in the next lesson. But that was what you would need to use for this one. So lesson 3, they just go over angle, and side angle side similarity. So again, this was just a quick recap of lesson 3.